first of all, there is a homework assignment due tonight. However, if you're here right now, you're going to see me do the entire assignment pretty much in class. So I've listed all of the problems here. I'm going to just cross them off as I do them. I'm going to be sprinkling them into my lecture, though, in different places. So you will have to compile them and get them in the correct order and all that good stuff. But I am going to do all these problems pretty much in class for you. So you won't have to worry about that. That needs to be turned in by tonight at midnight. I do have office hours after my last class, so after 5:30, if you're still wanting to follow up on any of this list of problems, you certainly can do that. Also, yesterday was crazy. We did not have Canvas for most of the day, but they finally got it back on, and I managed to send you, if you haven't checked, I did email you guys a extra credit quiz. Remember that because you introduced yourself at the start of the semester, every exam, there's going to be a video for points and there's going to be a quiz for points. You've already done the video. This is the quiz. And if you do this quiz, it is a double win for you because number one, you're going to get points for your exam. And number two, you're actually studying for the exam. Yes. Did I say you have to do it on paper? What I prefer, I'm not going to tell you how to do it. Do it however you want. I prefer if you do it like in the space that I made for you in the quiz rather than getting off onto your own paper. But I'll take it if it's on your own paper as well. Yeah. Anyway, that quiz needs to be turned in by tomorrow night at midnight. So you do have an extra day still to work on that. You can get up to 4 points for your midterm. And although those problems are going to take you a little bit of time, so just make sure you give the time to that if you're going to do it. But it will be, I think, helpful as both extra credit as well as being review for the exam. Okay, so that's coming up. Also, I am going to do another review session, especially after I saw the great turnout on Sunday. I'm going to do another review tomorrow evening at 7 p.m. I mentioned that I pretty much own this room. Well, except I don't own it on Wednesday nights. I found out that somebody else is in here tomorrow night. So I'm just going to do the review session tomorrow right out by my office. So I have a lot of space out there. So if you're interested, you can come by that. I did send out a video of it already, though. So if you don't want to come or you can't come or whatever, you're welcome to just watch the video that I sent you. I think over the weekend I sent that out to you guys already. But I'm going to be repeating mostly the same problems. Now, it turned out in my first class today, I didn't quite have time to totally go through the group work that I wanted to cover. So I might sprinkle in a couple of the questions from the group works into that review session as well. It won't be exactly the same as what I did on Sunday, but it should be pretty similar. So anyway, everybody is invited. Free of charge, 7 o'clock tomorrow night. If you want, just come down to my office and we will practice linear algebra problems until we've got it down. Yes, that's the plan. All of this is to say that we have an exam on Thursday, and that's kind of why it's a busy week. On Thursday, you'll have the entire class period to do this midterm. It's based on chapters 4, 5, and what we're going to focus on today, which is 6.1. And if you're trying to line it up with the group works and the homeworks, I've kind of put that here for you as well. We're going to try to do a little bit with group works 8 and 9 today in class, but it's not going to be a lot of time for that. So you may just have to study it up a little bit on your own. Or as I said, I might try and sprinkle it into the review session as well. So I think one way or the other, it'd be good to look at some of those problems. The homeworks for the exam would be 9 through 14. 14 being the one that we're working on now, and I'm going to do most of it with you in class throughout today's class. So that is the plan. Don't forget, there's 2 sample midterms, fully worked out solutions you can review with. I would definitely recommend that you try at least one of those, guys. The exam I'm going to give you will probably be similar in its structure, in sort of the balance of what topics are covered and all that. So obviously, it's going to be different questions, but it will be the same concepts for sure. So I highly recommend trying that out as well. Okay. I know it's a lot, but pick and choose. You don't have to do it all. Everything is optional. It's mostly just, you know yourself better than anybody, where your strong points are and where your weaker points are that you want to focus in on to get ready for Thursday. Okay, but I am here to help. I really do mean that. I want everybody to feel good about the material and to feel good going into Thursday's test. So just let me know anything I can do. Questions about any of that? That's just kind of my overview of where we're at. I am probably going out of town this coming weekend, so Friday through Sunday or ish, I'll probably cancel my office hours. I don't think I'll have too many requests for time on that. I will have something for you to do over the weekend again, like I usually do. It'll be another video to watch just on the next section, but it won't be too long. It'll be certainly not a 78-minute video like that one was. But I will have something for you to do over the weekend and just do it for Tuesday. But it won't be too bad. So that's kind of where we're at. All right. Well, let's spend today, most of today anyway, talking about section 6.1. I did start this last Thursday, but we only had a chance to really do a couple of quick examples. So I really want to spend more time on it now today. And this is the idea of a linear transformation. And T is going to be our notation for that. So T is going to be the notation for a linear transformation. And when I say that T is linear, that's just my shorthand for saying T is a linear transformation, right? So sometimes I'll just say T is linear. Remember, what it is at its fundamental core is it is a function. It is a function from one vector space to another. And so we use V and W kind of abstractly to represent the inputs and the outputs of that function. So you plug something in, the transformation spits something out. And they come from potentially two different universes, right? So I have two different vector spaces, V and W here. They could be the same, but they don't have to be. So maybe you're plugging in matrices and you're spitting out polynomials. Or maybe you're plugging in calculus functions and you're spitting out physics vectors, something like that. So just think about the universes that the vector spaces that we've mainly been working with, and you can imagine sort of what this is going to look like. Inputs and outputs. But this is more than just about having a function there. It's more than just inputs and outputs. To be a linear transformation, this function has to be very nicely behaved with respect to the vector space operations. So of course, in a vector space, we have addition and we have scalar multiplication. T must respect both of those operations in order for us to call it linear. And so I've reminded you here, T respecting addition, it just kind of looks like this, T of V1 plus V2. You have to be able to split that apart into T of V1 plus T of V2. All right. And then the scalar multiplication, if I have a scalar K and you apply T to K times a vector, well, you have to be able to factor that vector back out, pull it out in front. So the K has to come out. Sorry, factor that scalar out. So K is my scalar and you have to be able to factor that out. Okay, so this is the definition of a linear transformation. We did look at this last Thursday. I just wanted to get it back on the board again. With that, I am going to already jump into this homework. So I'm going to answer the true false item A right now. I'm going to be going out of order here. So you are going to have to compile these homework problems into the correct sequence for that list. That's going to be the hardest part, probably. But we are going to get around to talking about almost everything there. So on the true false part A, there is a statement, basically it's asking about this definition. And it just says that T is, I'm going to sort of paraphrase it here, guys. I'm just going to abbreviate it a little bit. T is linear if all of that stuff, I'm not going to write it down again, but what it says in the true false item is it says for some V1 and V2 in B, and for some K in the real numbers. That's what item A says. And if you just compare what's in blue with what I put up here already for the definition in the black writing, you can see that there is a one-word inconsistency here. And this is actually why this is a false statement. So this one is false. And the reason is that you notice that T has to respect the operations for all vectors and scalars. This says for some vectors and scalars. So that's just a one word change of meaning that changes the statement completely. So what you're going to want to say on this when you're writing up your homework is you're just going to want to say something like this: false for some should be for all. And if you make that little one word change, now you have the statement correct again. Okay, so it is false the way it was originally stated, but now it becomes true. Okay. So far, are we okay? This is just the definition. I want to make a couple of remarks that kind of follow off of that definition. And this is as good a time as any to make them. So there's two remarks, although I'm going to get sidetracked by the first remark for a little while before we go to the second one. So, my friends, if T respects addition, and if it respects scalar multiplication, then it actually respects all linear combinations. Linear combinations, after all, are just made up of addition and scalar multiplication. So the point is that from A and B above, from just those two properties above, what we can actually say is that if T is linear, then T respects not just addition and not just scalar multiplication, but it respects all linear combinations. Because linear combinations are just made out of expressions involving addition and scalar multiplication. So if I want to write that as a little equation for you here, guys, what I mean is if I took T and I applied it to the input C1 V1 plus C2 V2 plus dot 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 plus Cn Vn, if I wanted to transform an entire linear combination, which is what this is, right? This is what we call a linear combination. What we know is that T will respect both the addition and the scalar multiplication. And if you just apply both of those properties, you can totally bust this out. You can write it as C1 times T of V1 plus C2 times T of V2 and plus dot 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 plus Cn times T of Vn. You can completely bust it out like that. That's just kind of using both A and B simultaneously, right? I'm using the fact that T will respect both of my vector space operations in order to do that. Does that make sense? Questions so far? Well, if you're good with that, I'm actually ready to show you an example. So I'm not going to go to my second remark yet. I'm going to do a couple of examples that are focused on this remark. And the first example is actually number 31 from the homework. So as I said, I'm going to be using the homework to help me go over some of these ideas. So again, I'm going out of order on the homework here, but 31 just says, assume, I'll write it here for you. Assume that T is a transformation from P2 of R to P2 of R. But I want to assume that this is linear already. Let's say that for whatever reason, let's just say for whatever reason, we already know that T is linear. Okay, and then they give you some values here. So they tell you that T of 1 is equal to x plus 1. And then they tell you that T of x is equal to x squared minus 1. And then they tell you that T of x squared is equal to 3x plus 2. And what the problem is going to ask you then, the problem is going to say to find t of any quadratic polynomial. So in other words, t of ax squared plus bx plus c. That's what they want you to figure out. Again, this is pretty impressive. I only have to tell you what t does to 3 specific inputs. And then all of a sudden, based on that, I'm going to be able to figure out t of any other input into this transformation. That's pretty strong. That's actually taking just a small amount of information and building a huge conclusion out of it. But guys, when you look at ax squared plus bx plus c, you are looking at a linear combination of x squared, x, and 1, all of which were given. Right? So this is a super fast problem. Let me just do it right here for you. I'll show you exactly what I mean. Basically, what you can do is you can say, look, t of ax squared plus bx plus c. I can use the fact that t respects linear combinations to completely pull this thing apart. So I'll have a times t of x squared plus b times t of x plus c times t of 1. I can literally just bust that out. I can totally bust that apart. Okay, just a quick little warning. I'm not going to put this as part of the solution, so you don't necessarily need to write this down. But when I'm doing t of x squared, please be careful. That is not the same thing as trying to do like t of x quantity squared. In fact, I would argue that this doesn't even make sense. What you're trying to say here is that you're going to take some vector and square it. Well, in vector spaces, we can't do that. The only things we can do in a vector space are addition and scalar multiplication. This would be squaring a vector, which you cannot do. So just a little caution there. But that's okay, we don't need that because they already told us what t of x squared is, what t of x is, and what t of 1 is. So I can just use this given information and just plug it in. Let's go ahead and do that. Come back over here. So this just becomes a times t of x squared plus b times t of x plus c times t of 1. So this becomes a times the quantity 3x plus 2, because that was given to us, plus b times the quantity of x squared minus 1, and then plus c times the quantity of x plus 1. That's actually the whole answer. The only thing you could do, and it would be optional to even do it, but if you wanted to, a lot of times with polynomials, we try to organize the powers of x together. So you might say, well, I want to put the x squared term first, and that's fine. It would just be bx squared. And then the next term would be the x term, and I have a 3a here at the beginning, and I also have a plus c at the end. And so you could grab that coefficient and pull it out in front. And then the constant term would be 2a minus b and plus c. So if you just like expand out all those terms and group them by powers of x, it would look like this. But this is actually optional. If you just left it the first way, I would take that. That would certainly be correct. Does that look okay? Reasonable enough? So t respects linear combinations. And that includes something that looks like ax squared plus bx plus c. Questions at all? Let's actually do one more of those. The next one I want to do is actually slightly harder, and you'll see why in a second. Let me do it over here. So I'm going to do one more example. It's the same kind of idea, but as you'll see, it's slightly harder. This is actually number 33 on the homework. So I'm going to check that off as I go along here. I'm going to do number 33. This one is the same exact thing, except that the given information is maybe not quite as helpful in the beginning. So what they say here is assume that t goes from P2 of r to P2 of r the same exact setup. Assume that this is linear with, and now the assumptions this time are a little bit less helpful. I'll just put it that way. So they tell you that t of x squared minus 1 is equal to x squared plus x minus 3. And then they tell you that t of 2x is equal to 4x. And then they tell you that t of 3x plus 2 is equal to, I'm going to multiply that out and write it as 2x plus 6. So it's a similar problem, and they want to know the same exact thing. Find t of ax squared plus bx plus c. Same exact thing. Okay. So the philosophy behind this is exactly the same as the last problem. Like, in other words, my solution, I could just paste this. It starts off exactly the same way. The solution would be that what we want to do is bust this thing out using the fact that t respects linear combinations. So I can write it as a times t of x squared plus b times t of x plus c times t of 1. So I'm starting off exactly the same way as I did before. But on problem 31, they actually gave you these values directly in the question. And what you're noticing here is that the information that they gave you is actually not quite as directly, substitutable into the expression that I have. Is that a word? Substitutable. Okay. Yeah. So what we have to do is we have to figure out what is t of x squared, what is t of x, and what is t of 1. They did not give us those exact values. Does anybody see a way of figuring out what any of those might be from the information that's given to us here? Go ahead, Yasmin. Okay, this one, I can take t of x squared minus t of 1. Guys, in the blue writing, I'm going to work on these a little bit. So what Yasmin is suggesting is I can split that apart, and we absolutely can do that. That's right. And that will be eventually helpful to us. The problem is we don't know what either one of these is yet. Okay, is there anything else we could work with? Yes, Michelle. Okay, from which equation? T2x. Okay, we know what t of 2x is. This is actually the easiest one to work with. Because on the t of 2x, we already know that t respects the scalar multiplication. So I can just yank the 2 right out of it, you see. So pulling this 2 out in front, it's 2 times t of x equals 4x. So let me come over here and solve for t of x then. T of x, if I isolate the t of x, I just have to divide by 2, right? Just divide by 2. So t of x would be 4x divided by 2. Well, that's just 2x. So that's pretty straightforward. Great. So we already know what we're going to plug right there for t of x. But I still need to figure out what t of 1 is, and I still need to figure out what t of x squared is. And would anybody like to help me with that? Is there a suggestion how to do that? Go ahead.
You can do 3t of, using the last equation, you can do 3t of x plus 2t1.
I like that idea. Yeah, so we can bust apart the 3x plus 2. T will respect that expression. So I can pull out the 3 times t of x, and I can pull out the 2, which leaves me with t of 1. And the point here is that I already now know what t of x is. And so I can solve for t of 1. So let's see if we can do this. I might do this slightly in my head, guys, just to go a little faster with this. 2x plus 6, right? But I'm going to subtract off this one. To get t of 1 by itself, I have to subtract this off. Well, t of x was 2x. And so if I multiply that by 3, it's 6x. Maybe I should write it down. So the whole point is that this is 2x plus 6. That's on the right-hand side. Minus 3 times t of x, which was 2x, but then all divided by 2. So if I just solve for t of 1, in my equation. I went a little fast in the algebra there, but it's nothing deep. It's just rearranging the equation. This is, excuse me, this is what you're gonna end up with. And if you simplify this, you should get negative 2x plus 3. I think so. Negative 2x plus 3, yeah. So that's what you would get there. Okay, so that's t of 1. Now, once I know what t of 1 is, now we can go back to what Yasmin had originally suggested, which is I can take the first equation and solve for the t of x squared. So guys, it's just like the previous problem, except I'm having to do this little chicken scratch calculations first just to solve for the things I'm going to plug in here. Okay, so it's just a little bit more to it, but it's conceptually, you're doing the same thing. Conceptually, you're doing the same thing. So if I want to know what t of x squared is, I'm going to take this equation here, and I'm going to add the t of 1 to the other side. So t of 1, we just worked that out. It was negative 2x plus 3. And I'm going to add that to x squared plus x minus 3. That was already on the other side of the equal sign. Okay? And let's just simplify that slightly. Looks like the 3's actually cancel. And I just get x squared minus x by the time I get that all done. Okay, so my final answer, once I've got those values, now I go straight to my final answer, which is I just plug them in. So I just get a times x squared minus x plus b times 2x plus c times negative 2x plus 3. That would be the final thing with the values plugged in. So I have to spend a little bit of time to solve for t of x squared, solve for t of x, and solve for t of 1. So this is a common thing to see, for example, on an exam, would be I don't quite give you the information that you want directly, but you have to use the fact that t respects everything to create some equations that allow you to solve in blue for the stuff that you do want, that you can plug in. So it's a fairly common thing. Yeah, go ahead, Yasmin. I did. You could do that here too.
So it doesn't matter how we write it as long as it's.
Yeah, it's okay. I think on this one, I'm just gonna leave it like that. But yeah, you could rewrite it as a standard form polynomial easily enough. Okay, everybody okay with that? Any other questions on it? So this was all related to remark number 1, which is that t respects linear combinations. And in this case, the combinations are looking like polynomials. Okay, but really it's true in general. Everybody good? Okay, let's go to remark number 2. I have a second remark now. We'll kind of change subjects a little bit. And this is going to have to do with something called a zero vector check. So I don't know if you guys remember when, I hope you do remember actually, because we have a test coming up, but when we were learning about subspaces, you know, we said that for a subspace, you have to have closure under addition and scalar multiplication. But when we were doing that, I don't know if you remember, I always suggested that before you do anything else, you should just check the zero vector, right? Because if the zero vector is not in your set, then it's not a subspace and you can just stop immediately, right? So this is going to be kind of a similar theme where we have this check that we can kind of do quickly at the beginning. And if it fails immediately from the beginning, then you don't have to do any of the other verifications, right? So you can kind of put this on the back burner and just check this zero vector first. And what does the statement say? It's just this statement right here, guys. It just says, if t is linear, if t is actually linear, then if you were to transform the zero vector, if you plugged the zero vector into your function, you must get the zero vector out of it. Okay, you must get the zero vector out of it. And I'll just rephrase this maybe as well, so because the way we really use this result is, in other words, just to say it kind of a different way, if you transform the zero vector and you don't get zero, then you will know that t is actually not linear. That's just rephrasing what the line right above it says. For a linear transformation, right, when you plug in zero, it has to spit out zero. And there are actually some problems on the homework that are going to use this idea as well. This is another one of these things where as long as the test fails, it's game over. It cannot be a linear transformation. But if the test passes, then you have to go on and check if it respects the operations. Just the same way as the zero vector check that we had for subspaces. If that test failed, it was game over. But if that test passed, then you had to actually check, well, is the set closed under addition and scalar multiplication? So it's the same exact sort of framework here, just for a slightly different topic. I actually want to give you guys the reason for this zero vector check. I realize this is actually probably worth showing you guys. It's kind of theoretical, but it's not a big deal. But why is it that for a linear transformation, zero would have to be transformed to zero? Well, I can show you. If you actually want to transform the zero vector, right, you can play this little trick. It's a common trick in math, which is that you just add zero to whatever you had before, which of course does nothing. When you add zero to an expression, you're not changing the expression. So certainly t of zero would be the same as t of 0 plus 0, because, well, 0 plus 0 is 0. All right, well, but t respects this. So I can think of this as t of 0 plus t of 0. That's using property A over there, that t has to respect when I add two things together. Well, now what do you have? You have an object added to itself, and you end up with itself again. I ask you, how many things in this universe do you know that when you add it to itself, it's just itself? Well, 1 plus 1 is not 1. 5 plus 5 is not 5. Identity matrix plus identity matrix is not identity matrix. The only way that you can take a vector and add it to itself and just get the same thing back again is if it was the zero vector in the first place. So this just implies that what is this t of 0 vector that we have? It has to be the zero vector, and of course it's in the outputs of the transformation. So when I say zero vector, I mean zero vector of W in that context. So this blue writing is just explaining this second remark. It's explaining this zero vector check, right? So let's do a problem then from the homework that will be a nice, easy application of this. I think I'm going to do number 12. So I'm going out of order on the assignment, but I think number 12 is the one that is easiest to look at for an example. So this is an example, and I'm going to use number 12 to illustrate it. And here's what it says, guys, on number 12. T is a transformation from R2 to R2. And it is given with a formula. The formula is T of x1 comma x2. So I take two inputs because I'm in the vector space of R2. And I have to spit out two outputs. And the book gives us what we were supposed to do. X1 plus x2, comma 2. Right. And the question is basically asking well, it's actually just saying show that t is not linear. Show that t is not linear. That's all they want you to do. So before we actually take the time to see if it respects the operations, let's just look at this zero vector check. So I have a nice little zero vector check here. see this little white space here? I'm gonna write the whole answer in that little space. If you're in the back and you can't quite see, just stand up, because I don't want to start a whole new board just for an answer that's like half of a line. I'm just gonna try to plug in the zero vector and see what I get. Now, in this case, the zero vector is 0, 0. So you just put in zeros for all those x's, and when you evaluate that into the function that was given, we get 0, 2. That's the output. Well, that's not the zero vector anymore, right? So this is not equal to the zero vector. So there you go. That's the whole solution. I guess I'll write one more line. The zero vector check fails. And you can stop as soon as that zero vector check fails. So you don't have to get any more messy than that. Of course, it's not going to respect addition. You take 2 points that both have a 2 in the second slot and you add them together. Well, that'll end up being a 4, because 2 plus 2 is 4. Well, 4 will be the wrong number to have in the second slot for the t of anything. It's not going to work. But this is easier. This is faster. That's the fast way to kind of get a counterexample, or to show that it doesn't form a linear transformation. Does this make sense? Questions here, guys? So I have to pair that up, if everybody's good so far. I have to pair that up with an example that reminds you of my warning. Because I did have a warning about this zero vector test, and I just want to get it into our notes as well. And the warning is what I already stated. Namely, that if this zero vector check passes, it doesn't mean that t is linear. If the zero vector check passes, then we have to go on and confirm whether it respects the operations. And I can give you an example. So this is a warning example. This one is actually not from the homework. I'm just going to make up one that's kind of a separate one. It's a great example, and it's one that I think you guys will all believe, which is that I'm going to define t to go from the n by n matrices to the real numbers via the equation. So I'm going to give you the formula here, guys. We're going to plug in a square matrix A, and I am going to spit out one number. This is the real numbers, so that's just a single number, and I'm going to spit out the determinant of that matrix. It's a square matrix, so I can take that determinant. And I'm going to ask the question, is t linear? Is t linear? This is the question. And as I just got done explaining, I like to do this zero vector check first, because if it fails, we can stop immediately, like we did there, right? So let's just check that. Let's just check that. So for my solution, I'm going to do the zero vector check. By the way, guys, the zero vector check is not required to do it, right? You don't have to do it. If it passes, it's not going to prove anything. You're still going to have to do all of the same work. But the reason for doing this is that if this fails, then we can quickly conclude that t is not linear, like we did on that last example. But let's just try it here. What happens when I plug in my zero vector? Now, the zero vector in the world of the n by n matrices would just be the matrix of all zeros. What is the determinant of the all zero matrix? Really? All zero, you better get 0. Yeah, for sure. So guys, this zero vector check passes. T of 0 is 0. So this one passes. Oops, I gotta spell better. This passes. It actually passes the zero vector check. But that does not mean that t is linear. To be linear, I really have my definition here that I have to fall back on. And so I have to ask myself, will this determinant function, will it respect addition and scalar multiplication? So let's just try it. Let's just see what happens when I try to verify that t respects addition. that would look something like this. I have to take two vectors, which would be maybe A and B, and I have to add them together. Right? Now, if you transform A plus B, then according to this formula, the result should be the determinant of A plus B. So everywhere I have an A, I'm now plugging in A plus B on both sides. And the question is that the same thing as doing T of A plus T of B? No. We actually had this in a group work way back in chapter 3 when we were studying determinants. This is kind of an old idea, but one of the things that we said back in chapter 3 is that determinants do not play nice with addition. They do not. They do not respect addition. So this is not equal to the determinant of A plus the determinant of B. In general, there's no formula for the determinant of A plus B. And you would have needed that to be true if you were trying to get this split apart. If you had been trying to get the T of A plus T of B, which is on the right-hand side, if you were trying to get that to be your final line, you would have needed to make all of these things work, and we have a problem in the middle that we cannot get around. This fails to be respecting addition. It fails to respect addition. Now, you can go back to your group work or remember from the first part of the semester an example of this. You could probably write down a couple of 2x2 matrices where the determinant of A plus B is not the same as the determinant of A plus the determinant of B. That's something I won't go back over again right now, but we have talked about that before. So this thing is a no-go. It's not going, even though it passes the zero vector check, it ends up not being a linear transformation. I should put no here. It is not a linear transformation at this point. And we don't even need to look at the scalar multiplication, because as soon as this property does not hold, then I don't care how many other wonderful properties you have, it's not linear. If any one thing goes wrong, it's not linear. Yes, question?
Did we also say earlier in the semester that the determinant of 0 is non-invertible, so it's not linear?
Whether there's an invertible matrix or not is actually not relevant to whether T is linear. There's not really a connection between being linear and being invertible. But you are right. We did say that for a matrix, if the determinant was 0, then it's not invertible. But see, this matrix, this is just the whole, this is all n by n matrices, whether they're invertible or not. So I've plugged in a matrix that's not invertible, but it doesn't really matter whether it's invertible or not. Yeah. Okay. All right, so that's my little zero vector warning. But that zero vector check is a nice one. It is a nice one. However, I'm happy to report that even though determinants do not, but maybe this is why the guy said down with determinants. I don't know. I still can't figure out what he doesn't like about them. Well, this is one bad thing, I suppose. The determinant function is not linear, but there's something even better than determinants that is linear, and is, I say it's better because it's related to my personal job security. And that is that I would probably not have this job if calculus wasn't linear. By that, I mean derivatives, integrals. So determinants don't play nice, but derivatives do, and integrals do. And because of that, it actually makes sense to teach differential equations and linear algebra in the same class. If derivatives did not respect addition, or integrals did not respect addition, you'd start to wonder, why are we putting these two classes together? All this linear algebra doesn't even work for derivatives and integrals. Why would we want to, put them together in a differential equations class? Well, it is because actually derivatives and integrals do play nice with addition and scalar multiplication. And one of those is number 6 from the homework. So we're going to go back to the homework now, and I'm going to show you what I mean. And I'm so glad I have a job. Because of this, it keeps me gainfully employed. So here we go. Number 6 from the homework is the following problem. Show that T is linear. And I'm gonna write it down for you guys. This is T is gonna be a function that goes from C of AB over to the real numbers via, let me just remind you, C of AB, this is just the universe of calculus functions on the interval from A to B. And of course, the real numbers is just spitting out a number. So I'm going to plug in, let me use the same notation as the book. I'm gonna plug in my function F here. I'm gonna take T of F, and the way I'm gonna do it, guys, is I'm going to integrate F of X dx from A to B. So here's what I was just saying, that integrals, at least they do respect the vector space operations, and we're gonna show that right here. Okay, so that's a good thing, right? This is a good thing. I might need just a little bit more room. I'm not actually going to stop and do the zero vector check on this, although you could. I'm not gonna do that because I already know that it passes. And if it passes, then that doesn't really help me because I just still have to do all of the rest of the work. So let's just go straight into the two properties of a linear transformation here. Just write them down and see if everybody understands this, okay? We doing so far so good? Good. Okay, so let's give the solution here. And I'm gonna start by just showing that T respects addition. So T respects addition. Let's just see how this one is going to look. So I have to take two functions, just so I use notation that's kind of compatible with my inputs. Let's just call them F and G. And I want to try to figure this out. So T of F plus G. Well, according to my formula, I'm just going to integrate whatever it was that I plugged in. So I'm going to integrate F plus G of X dx. And I do that from A to B. It's just some definite integral. It'll have some numerical value as an output. Okay. My goal with this sort of thing is to get these split apart. Okay, but to show some work on that, I first need to sort of figure out, well, what is F plus G of X? It's actually just F of X plus G of X dx. I'm going to use some brackets to kind of make that a little more clear. So you're just adding the two functions inside those brackets, F of X plus G of X. So if you have two things added together and you wanted to integrate them, what would you probably do? Separate them out, right? Just integrate them separately, right? This is the key step. I can actually do that. I can break this up as the integral of F of X plus the integral of G of X. That's it. That's the whole point. And the first integral just gives me my T of F, and the second integral just gives me my T of G. And that's the whole story. Put a little check and we're good. So T does respect addition. We did one of these last Thursday and I also formatted it like this, guys. I do want to try to get you into the good habit of not writing on both sides of these equal signs. So once you kind of start making your chain of steps from one to the next, let's do them in a single file column. Let's put those equal signs in there, right? Don't tempt me to pull out my red pen. Just this thing equals this thing equals this thing equals this thing, and nothing on the left side. Just try to format it just like that. Okay? So this is T respecting addition. Is everybody following that? Okay, I'm going to be quiet for about 1 minute. I would like you guys to try to write down in your notes how we could write up the verification that T respects scalar multiplication. So go ahead. I'm going to shut my mouth for a minute. I'll let you guys try to write it down and then we'll see what you can do. Remember that I usually like to use K for my scalar. K is good scalar. Anybody think they might have it? Anybody confident enough to come up and put it up there for me? Maybe want to be brave? Nobody's brave.
I got to Dr. Ed.
You got it?
I got
Let's
it.
go, Eric.
I hope so. This will be all over YouTube.
No way.
You're gonna be famous. You're gonna be famous one way or the other, whether you like it.
Oh, okay.
That's okay. We'll keep you on the straight and narrow. We'll fix it up if you need help.
All right, then.
Go for it.
What's up, y'all? We're gonna check With the respect to multiplication. So we're gonna do. Um.
Okay, T of K times F. Yes, it's good.
Looks good.
Whew, good start. No pressure. Looking good. So we got an integral from A to B. Nice. Okay,
Yeah.
let's check it off. He's got the check mark there. That's pretty confident.
Ooh, I'll put 2 just in case.
What do you guys, I can tell you one thing. I haven't even looked at what he wrote yet, but I love the formatting.
Oh, yeah.
Yeah, we got the white space going on the left side. We've got all of our equal signs written down. That's all good stuff. And what do you guys think? Does it all look good to you? Is that what everybody else got? Yeah, that looks great. Thank you, Adrian. Yay. Give him a round of applause.
Like and subscribe.
Yeah, so this is it. You just pull the K out. Of course, we know with integration that constants can be factored out. And so you just get your conclusion exactly the way you want it. I love it. Okay. Looks good. Looks good. Okay, that's number 6. So I think we're rolling pretty good on that. Let's try, I mentioned that calculus respects these 2 operations. So we've got an example that shows it for integrals. What about for derivatives? Well, derivatives is handled by number 3. So I'm going to do number 3 next. Let's try number 3. Maybe I'll put it over here. Let me write it down for you guys. Let's see. This one, they give you t, which is going from C2 of I over to C0 of I. And the formula for this one is that T of Y, so Y is going to be my input right now. And we're going to output Y double prime plus A1 times Y prime plus A2 times Y. And what I'm hoping to do here, guys, is we're going to try to show that T is linear again. I'm going to try to show that T is linear. So derivatives also respect addition and scalar multiplication. Again, I'll leave out the 0 vector check because we know that that's going to pass since this is asking us to show that it does work. I'm just going to jump right into the two properties here. So let's check for the solution. I'm going to start off by showing that T respects addition. Okay. And they gave you Y as the function here, but you don't have to use Y. You can use F and G again. Anything that's like a notation compatible with the vector space. I probably wouldn't use like A and B because I think of matrices. When I'm thinking of A's and B's, I'm thinking of matrices, and I wouldn't want to get myself thinking that this has anything to do with matrices. Right, so try to use inputs that make sense in the context of whatever the example is. Right, and so all I'm going to do is plug this into my formula, right? So if I plug in F plus G, well, that's just F plus G double prime plus A1 times F plus G prime plus A2 times the quantity F plus G. So we can literally just spell it out straight off of the formula here. Oh, by the way, I forgot to mention, some students have been asking me about these notations at the top. It turns out they really don't get involved at all in what we're doing. This just means you have some interval and you've got to be able to take two derivatives. That's what the two stands for. You've got to be able to take two derivatives of whatever you're putting in. Obviously, you see two derivatives coming out here, so it makes sense that you have to be able to take those derivatives. That's all that that really means. It's not really a part of the substance of the solution that you have to write down. What do you want me to do with this? So you see some of you writing it already. What am I gonna do next? Distribute the derivatives, exactly. And you probably did this in your calculus class. They probably showed you that, yeah, derivatives, they respect addition. So you can distribute all of these terms out, right? And get a whole big, long string of about 6 terms there, right? And once I've got them all sort of laid out individually like that, what do I want to do next, do you think?
Group your variables.
Yeah, group the variables. Let's just say that you have a brain fog for a sudden a minute, and you're like, I don't know what to do now. You got all these terms, or what am I supposed to do? It is okay to kind of think from the end. You could think, well, eventually I want to get this at the bottom. And that's T of F in the front and T of G in the back. That would give me an idea that I should put all of the F stuff in the front and all of the G stuff in the back. So I can reorganize these terms and put all of the terms that involve F in the front. So that's what I'm going to do right here, guys. F double prime plus A1 F prime plus A2 F. And then to that, we're going to add the second one, which is G double prime plus A1 G prime plus A2 G, right? So just anything involving F goes to the front, anything involving G goes to the back, and lo and behold, what you now have is exactly T of F added to T of G. Pretty much as is. You don't even have to change that a bit. Yeah. That look okay? No surprises there, guys. Everything about that is just playing right along with how it's always worked since you took calculus. I'll quickly do the scalar multiplication and then we're going to move on. But this is an easy one as well. This is just where you have to transform, let's say, K times F. Right? I'm sure all of you could do this by now. We've practiced enough, but I'll just write it out just to be complete. So it would be KF double prime plus A1 times KF prime plus A2 times KF. So you're just plugging in the KF everywhere you had the Y in the original setup of this. Okay? My ultimate goal is to get the K outside in front. So I see these expressions and I hopefully remember from my calculus days that constants just come along for the ride when you take derivatives. Nothing has to be changed. So you just literally pull them out as if nothing is happening. And so you're going to end up with those terms like so. And what's the obvious next step here?
Okay.
Got a K in every one of my terms. I'm going to pull it out. Exactly. So we factor out the K. It leaves me with F double prime plus A1 times F prime plus A2 times F. That's exactly right. And so now the K is outside where we want it, and the T of F is what's in the brackets. So this is also good. Put our check marks here. Everything is being confirmed. Everything is being confirmed. Okay. Hopefully. That decent for now? Okay. Well, we have about 5 more problems to go here. These last 5 problems are all about the same topic, which is something I haven't talked about yet today. So I'm going to do it now. I'm going to at least introduce it now, and we'll take a little break. But let me just at least get this into your head a little bit so that you're kind of thinking about it as we go along. I get my page open. There we go. There is an entire family of linear transformations that all kind of come under the umbrella of one concept. And it's important enough that we need to sort of have some notes on this before we even get into the homework examples. So I'm going to call this an important example. It's not gonna take very long to explain it, though. I promise. It's actually not that bad. I just do want to do this somewhat formally so that everybody has some good notes to look at on this. So here's the idea. Here is the idea. I am going to fix an M by N matrix, capital A. So could just be any matrix. Gonna fix this matrix. And I'm gonna do something with this matrix that's different than anything I've ever done with matrices so far this semester. And that is, I am going to use and view this matrix as itself being a function. The matrix is going to be the vehicle that creates the function. And it's just so gonna happen that it's gonna respect the vector space operations, which means that I'm going to be able to view a matrix as being the driver of a linear transformation. We can actually create a linear transformation out of it. I'm going to show you how to do that. So we can view A as a linear transformation. That's very weird, right? We haven't normally been thinking about the matrix as being a function. Right, we think about the matrix as being, solving systems of equations. We've thought about the matrices as being vectors in a vector space, right? But as a function, that's a little bit different. We can view A as a linear transformation. In other words, there is a T that we can associate with it. I'm going to show you how to do this. This is super easy. It will be a transformation from Rn to Rm. And I want to be very careful with that because sometimes people get this mixed up. The M by N matrix creates a transformation from Rn back to Rm. So the roles of the M and the N are kind of swapped. You see that? Right? The M rows and the N columns gives you a transformation from Rn to Rm. And what is the formula? Like, how does it work? Here it is, guys. You're going to plug in your vector x, which is in Rn, and the output is going to be simply A times x. Let's put a box on this one. This is the matrix being used as a driver of a linear transformation. Let me make sure you guys all believe me on this. Let's see, x right here, it lives in Rn. So I can view that as an n by 1 column. When you're thinking of plugging this vector in, I want you to think about it as being put as a single column. Now, if the matrix A was M by N, and I'm doing, this is multiplication here, guys. If I'm multiplying it by X, which is N by 1, can somebody remind me in terms of sizes of matrix multiplication, what is the resulting size of the product of those two things? One more time. M by 1, exactly. Thank you, Joel. It's M by 1, which is Rm, right? That is the vector space with M slots. So this is exactly how this is going to work. Right, we plug in a vector with N slots, we throw it into this matrix, and by throw it in, I mean we multiply by this matrix, and it spits out something that has M slots. And most of these 5 homework problems are just going to be examples of this, okay? Before we actually do those examples, though, I owe you a little bit of a justification because I said that we can view A as a linear transformation. And so everybody has to be convinced that this actually is linear. So just like these earlier examples show that T is linear, I should show that this is linear also. I'm going to do it right now. The good news about this is that if I show it right now, you guys never have to doubt it again. The only person in this room who will ever have to reconvince themselves will be me next semester when I teach the class again, right? So we do need to technically show that this is linear. So I'm going to do that. So note that T is linear. I'm gonna show it right here. T respects addition. Let's try to write that down and just, there's nothing about this that should be terribly messy. If I have T of, let's say, x plus y. So I take two vectors, I'm just following my property A right here. I'm showing that T respects addition. So if I want to do T of x plus y, well, my formula tells me, if you believe this, this is what I'm giving you. My formula tells me whatever you plugged in to your function, just multiply it by A. So let's do that. Let's just take A and multiply it by whatever I plugged in, which was x plus y right now. Now, we learned when we were kind of doing basics with matrices that matrices do respect the distributive property. You can split this apart. This is just AX plus AY. A times X plus A times Y. And sure enough, guys, that's all there is to it. This is T of X plus T of Y. Just that simple. So we'll put our little check mark on that one. T does respect addition. And we don't need a lot of room, so I'm going to squeeze it right here, guys. T also respects scalar multiplication. And again, I'm just going to very quickly write that down. So if I take K times X and I transform it, I'm going to try to show you, it's going to take me maybe 30 seconds if I really go slow. I'm going to try to show you that T respects scalar multiplication. If I want to transform anything, I use that box equation, which just says put A in front of it. So I just get A times KX. Now, my goal is to get the K outside in front. We do have to be a little bit cautious because we learned earlier this semester that when you're talking about multiplying with matrices, the order does matter. You can't switch the order of two matrices that are being multiplied together. But what I want to point out here, guys, is that this K right here is not a matrix. It's just a scalar. It's just a number. And when you have a number there, there's no harm at all in switching it with the matrix. I'm going to pull it out in front and leave the AX together, like so. Yeah, and as soon as I do that, well, then I'm good to go. Then I just have K times T of X, and everything is hunky-dory from there. It does respect scalar multiplication. So anytime you want to make a linear transformation, I've got a great plan. Just write down any matrix you want and make this equation with that matrix. That will be guaranteed to be a linear transformation. I just verified everything over here once and for all. I don't ever have to check it again and wonder about it. It's automatically going to be true. Okay. By the way, there's a name for this. Maybe in the notes we should come back. There's a name for a transformation that looks like this. It's called a matrix transformation. So this is a matrix. It's a linear transformation, but specifically we are using a matrix to make it run. So we're going to call it a matrix transformation. And what we've just verified is that this is always linear. This is always linear. Right, so a matrix transformation is always going to be linear. Let's try one example here and then we'll take a little break. And for this example, I'm going to go back to the homework again. I'm going to look at number 15 from the homework assignment. Let's figure out like what kind of questions are they going to ask us about this. So on number 15, they give you a transformation formula. So they give you this formula here, guys, T of x1 comma x2. And the formula they give us is x1 plus 3x2 comma 2x1 minus 7x2, comma, x1. And what they ask us to do on this problem is they ask us to find the matrix of T. So in other words, they did not give us the matrix. I keep talking about how we have to have some matrix. Okay. Well, they did not give us that matrix. They're actually asking us to figure out what that matrix is based on the formula. And to do this, we don't really have much effort to go to. It's actually quite easy. To do this, the first thing I want to point out is, can anybody tell me, in this example, the T is going from R what to R what? Can you see it? What the M and, or sorry, what the N and the M are here? How many inputs, how many outputs? It's really what we're talking about, right? The number of slots is telling me like R whatever. How many slots am I putting in?
2,
2. So this should be a 2. And then how many slots am I spitting out?
3.
3, right? So I'm going from R2 to R3. Based on that, can you already tell me what the size of this matrix is going to end up needing to be? 3 by 2. Yes, I agree, because remember, I've got it over here. The M by N is related to the Rn and Rm here. So the N is 2 and the M is 3, right? So this is going to be 3 by 2. 3 by 2. Now let's figure out what the numbers are that go in here. You need to have 6 numbers to put in here. And if you're thinking, well, I see about 6 numbers up here, you'd be absolutely right. This is not a hard thing to do, right? You're just gonna grab these numbers here and put them into the matrix. But I just wanna make sure we get it right as to how they're going into this matrix. Remember, if you multiply this by x1, x2, and I realize here, guys, in the question, they wrote the x1, x2 as a row, but you need to render it as a column with n rows and only one single column, right? So I just have to kind of take the x1 and x2 and plant it as a vertical column. And I know that when I do this, this is just a times x right here. That's supposed to be giving me my output of my transformation. So what I'm supposed to get over here is x1 plus 3x2, and then 2x1 minus 7x2, and then x1. My point, guys, is that even though it was presented as a row, the question is kind of everything's been laid out horizontally. We need to view the inputs and outputs as filling columns, not rows. Well, can somebody tell me what numbers to put? Like what numbers do I need to put on the first row in order for it to come out like this? You're remembering your dot product matrix multiplication, right? So what numbers do I need to put on the first row? 1 and 3, right? What numbers do I need to put on the second row? 2 and -7. Wonderful. What about the third row? 1 and 0. Guys, it's just that easy. It's just that easy. You could just write this down literally by looking at the formula. Right? So it's actually very easy to write down this matrix if they give you the formula first, which is exactly what they did on problem 15 and I think 17 as well. Now, this can be done the other way around, where they actually give you the matrix first and then ask you to write down the formula. So this works both ways. It's a two-way street. Given a matrix, we can write down the transformation T of x. Or, like what we just did right now, given T of x, we can write down the matrix. It goes both ways. So let's just chew on that for, take a 10-minute break or so. Chew on it for 10 minutes, and then we'll pick this up. And I'm just going to finish those last couple of homework problems after the break. And then we'll be good to go for that. And I think we'll be good to go for the whole section. So let's just go ahead and I'll give you a chance to stretch your legs if you'd like, and step outside, get some fresh air. So. See you in a few minutes. Doing okay? All right.
Oh, God. Trying to trying to go to war in this game.
Dude, you look at this.
Did he get me on the no way. No. This kid.
Yo, I knew it.
He's obsessed with it.
Huh?
I'm sorry. No, put in my car, but it's all in my car. I don't know. The one next to TSU. I came late, so I didn't think I was gonna come from again. Fuck, no, I can't be on tonight. That was good though. You missed out. Should have ditched. Not really, I don't think so. I did have a lab on Thompson. Yeah, either one lecture, one day's a lecture, the other one's like. Your outies? Right then, dude. I'll see you. Oh, I'll see you. I don't know which one. Sometime? Sure. See you, Brody. I mean, it's just you now.
What if this chair is sharp enough to?
What? No. You're gonna do this without Brandon's class.
My face was covering half the ear.
You're gonna do that without Brandon's class.
It's like, it's raised by with the D, so I can move on to 381. No, to 4071, 323. For computer.
Yeah.
This is a prerequisite for those two classes. Once I get that, I get all the other shit done. I can go to Florida graduate.
Oh, yeah.
And then you can say, I got it. Yeah. And I can just go, oh, okay, so now that everything else is out of the way, I can come back to this. Or I can. Oh my God.
Okay, chapter 5 was what comes after closures, so that one's substitute. Cost basically the rest. What?
Yeah.
You're lying. Let's see. Oh, the left moving. Oh, yeah.
Bro, you're not gonna take these in.
What?
Like the notes.
Yeah. No way.
I'm glad.
Yeah.
No,
Oh. Oh, yeah.
It's the one you said.
Oh, did I miss you? Oh.
That's all. Oh,
What, that's so lucky, once it cried out, we have one over there. No, that's like my last.
Some of them, I'm sure. Yeah, probably won't go, there's a lot of them there, and there's a lot.
Bridge, honestly, yes.
No.
Right.
Oh, right. She's not here.
I don't think so, no.
Okay, okay, well, that's.
That's.
Bless you.
Oh, no, you're.
This guy's gas.
I never. Yeah.
No, you said.
No, I'm saying.
Oh.
I thought about it, can't believe you left.
It can be racist.
I think if Dave.
Yes, we're probably not gonna have time to do this. At least give my.
Don't tell me.
Actually, you're right. Stanford is not all-
Alright.
And then it mentions here that gives them.
I don't think. Oh, okay, that's not how I got it. Sorry, this overheard.
Oh, yeah. If there's two vectors. Do I check if it's, Oh, you're the red, Well, that's wrong. All I know is you can't tell me that it's.
Bro, you're gonna make me want
If it's a steam. Then you can't do that, because that's three.
Yeah.
Watch.
Oh, yeah, that's what we do. I told you, I'm like, oh, really? The smart fashion in my head. So it's okay. We tried to do it, but now we have to run out of space.
No, you have one in the matrix.
Oh, yeah. I did my.
Yeah.
I did my time. You go, you go. Yeah. So
But they're performing here.
I got 16.
Guys, today we've got just about everybody made it back. Great to see all of you here and hopefully it's making pretty decent sense overall. We don't have a lot of time. I just passed out a couple of group works. I'm gonna try to give you a couple minutes to look at a couple of those at the end of our class today, but more likely I will probably add them to the review session topics. Tomorrow night, I may go over some of those group works. My first class, when I turned them loose on it, they were having a little bit of trouble with a couple of those problems. So I will definitely try to circle back to them. If I don't do it in the next 20 minutes, we'll have to find another time to make sure we get through with that. But what I really want to do first is try to finish talking about anything left over from 6.1, and I'm almost there. We were talking about these matrix transformations. And the idea was that there's basically a correspondence between an M by N matrix and a transformation from Rn to Rm. And we did the example right before the break, which I tried to keep on the board here, where I gave you the transformation and just asked you to write down the matrix, right? So let me just kind of clear some of this clutter out of the way. Here was the matrix that we ended up with at the end of this problem. So I gave you this formula and you wrote down this matrix. So you're probably looking at this and you're probably thinking, oh my gosh, it's so easy. It's easy. I just take this formula. I don't even have to show any work. I just go straight to the answer. I just grab the 6 numbers that are up here and throw them into here. Well, it's actually not always quite this easy. It's not always this easy. The reason that this one was so easy was because they gave you the full-blown formula all the way written out. So they gave you T of any input whatsoever, right? But let's do number 28 from the homework, which I've put over here. It's not quite as easy because they did not give you a formula for T. They did not tell you what T of x1, x2, x3, x4 is. Instead, they gave you T of some specific values. And then we have to find the matrix for that. Find the matrix that goes with T. So I want to, before we actually solve that problem, guys, just in general, I want to write down, maybe I'll do it right here, what the formula is for the matrix, okay? The way that this matrix works, and it's an M by N matrix always, is, well, actually, you might be able to see, I've kept this example up here. You might be able to see that this matrix could be sort of filled out almost column by column. The first column is actually, so if I actually, let's go back to this example. If I actually work out T of 1, 0 right here, in this formula. If I put a 1 everywhere that I see the x1 and I put a 0 everywhere that I see the x2. So plug in 1 and 0, and what do I get? 1, 2, and 1. All right? I get 1, 2, and 1. I'm talking about this previous example. Okay? Do you see the 1, the 2, and the 1 in the matrix?
Yeah.
It's just this first column, actually. Right? And then if I do the other standard vector, which is 0 and 1, now I'm going to plug in 0 for the first input and a 1 for the second input. Well, if I put 0 for x1 and I put 1 for x2, look what numbers I'm getting. 3, -7, and 0. 3, -7, and 0. And if you look at this matrix, you can see that my second column is in fact 3, -7, and 0. The columns of A are literally just the outputs of transforming the standard vectors of Rn. And you just lay them out in the columns. So I can now finish this little note. Basically, in general, if you want to figure out what your matrix is, the first column is just T of 1, 0, da, 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 0, right? And then the second column will be T of 0, 1, 0, 0, 0, da, 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 right? And you just go column by column like this. These bars are just sort of separating out my columns for me. The last column would be T of 0, 0, da, 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 and then a 1 at the end of it. And you literally just transform those standard basis vectors, just like that. So you should definitely have this kind of highlighted into your notes. How do you find the matrix of T? You just transform the standard basis vectors. Now, if they give you, right, if they give you the full formula, like right here, no big deal, right? We figured out this matrix by just reading off the 6 numbers out of this expression. We didn't need to do it column by column. The 1 and the 3 just went in the first row. The 2 and the -7 went into the second row, and the 1 and the 0 went into the third row. And we could just glance at this formula and write that down. We didn't really need to come over here and do this calculation on the side. But there might be situations where you don't have the full-blown formula, like problem 28. They did not give you the general formula for T of any input. They just happen to give you 4 random inputs here with the corresponding outputs, and they already think you should be able to write down the whole matrix. So let's see if we can do it. Let's see if we can do it based on this general form that I just gave you. So now I'm going to do the solution, and I think I'm going to do it right here, right next to the formula I just wrote down. First of all, can somebody tell me what size matrix I should be looking for on problem 28? Right, my transformation goes from R4 to R2. So again, just to reiterate again, from R4 to R2, that would mean that M is 2 and N is 4. It's a 2 by 4 matrix. It is a 2 by 4 matrix. So I'll give 2 rows and 4 columns. And I just explained how to do the columns of this matrix. The first column should just be T of 1, 0, 0, 0. Well, they gave that to us. They gave that to us. It's just 3 and -2. So we just put that into the first column of the matrix. Okay. Now the second column is supposed to be T of 0, 1, 0, 0. Do we have that?
No.
Well, they did not give it to us. Ooh, that's unfortunate. They did not tell us T of 0, 1, 0, 0. They gave us a bunch of other values. So can we figure out what T of 0, 1, 0, 0 should have been from what they did tell us? We better, otherwise I don't know how to do the problem. Right? Is there a way to sort of make 0, 1, 0, 0 out of what's already here? Go ahead.
Can you take T of 1, 1, 0, 0 and subtract T of 1, 0, 0, 0?
That's exactly right, guys. T respects subtraction, right? So if I do the subtraction of the second one minus the first one, so I'll just write this over here in blue. T of 1, 1, 0, 0 minus T of 1, 0, 0, 0. If you subtract those slot by slot, you're just gonna get T of 0, 1, 0, 0. So T will respect that subtraction. And so that just means that to figure this out, I just need to take the second one minus the first one. Well, that would be 5, 1 minus 3, -2. So I'm just gonna subtract those points, 5, 1, and I'm gonna subtract 3, -2, and what does that give me? 2, 3, 2, 3, and that is what goes in the second column. That is T of 0, 1, 0, 0. Okay? Let's do the third column. The third column should be the T of 0, 0, 1, 0. You see how to make that out of what's here? Let me try and write it up nicely here. So I'm trying to figure out T of 0, 0, 1, 0. Can I build that vector out of what is given to me? Because I don't see 0, 0, 1, 0 here. Can I make it though from what is here? How? Go ahead, Dylan.
Subtract the third one from the second one.
Third one minus the second one, exactly, beautiful. So we just take T of 1, 1, 1, 0 minus T of 1, 1, 0, 0. Right? Because T is gonna respect this subtraction. So T of that minus T of that is equal to T of that. And they gave us these values. So we have a -1, 0 minus a 5, 1. And so it's just the third one minus the second one. Third one minus the second one, and when I plug that into here, I'm gonna get -6 and -1. And that goes into the third column of my matrix. Okay, and then how about the last one, guys? What is T of 0, 0, 0, 1 going to be?
The fourth minus the third.
Exactly, we're gonna get the fourth one, I'll put it right here, guys, just chicken scratch on my board. The last vector is just simply the fourth one, which was 2, 2, minus the third one, which was -1, 0. And when we clean that up slot by slot, we're going to get 3, 2. That is what we put into the last column here. 3, 2. And there's your matrix. And now from this matrix, we could write down T of anything. Because this matrix, if I give you the matrix, once I have the matrix, I have the entire transformation formula. Right? So yeah, that's how 28 works. That's how 28 works. Let me just make sure my last point that I just made is 100% clear. If I give you the matrix, you have the entire transformation formula. Right? We don't have the entire formula here, guys. I only have 4 values. Right? But the R4 is an enormous vector space. There's so many other points. What is T of 6, 7, 8, 9? What is T of 12, 13, 14, 15? I could take any 4 numbers and I would want to know what is T of that, right? Somehow, just from these 4 pieces of information, we're able to construct this matrix, which then allows us to find T of any other point. I love it. I love it. People who are into computer graphics should especially love this. If you're trying to design some image that's moving on your pixels of your screen, and I tell you that this pixel moves here and this pixel moves there, I just tell you those 2 things alone, right? Then assuming that there's some sort of a linear transformation of the points on this screen, then from the information about 2 pixels, I can reconstruct where every single pixel gets transformed onto that screen. It's an incredibly powerful idea. And it's all because the transformation is linear. In this case, I need to know where 4 pixels, specific pixels get moved, and then I can completely figure out my transformation. So amazing, so amazing. So So let me show you what I mean by completely figure out my transformation by doing problem, I think I'm gonna do number 20 from that assignment there. Let's do number 20, and then I think I'm probably gonna actually make you guys do 17 and 23 on your own, which will take you all of 1 minute probably each at the most. So number 20, this is another example. This is really fast. Here's the matrix A. So they give you this matrix, right? 2, -1, 5, and then 3, 1, and -2. They give you that. And then they just ask you to find the linear transformation T. It's just the opposite of what we just did. Here, I gave you the linear transformation and I asked you to find the matrix. Now I'm gonna give you the matrix first and ask you to write down the transformation. And for the solution, let me go back to blue for my solution notation. The first thing I like to write down is this is a transformation from R what to R what? How many inputs and how many outputs, guys? Yeah, if we look at the size of the matrix, the original matrix is 2 by 3. So the M and the N are 2 and 3, so the transformation is gonna go from R3 back to R2. It switches the order of the M and the N, and we go back from R3 to R2. And what I have to do is I have to give you the formula. I'm gonna plug in 3 inputs and I'm gonna output 2 outputs. So let's write it down. The 3 inputs, I'm gonna call them X, Y, and Z. Now, by the way, this is completely up to you. You don't have to use X, Y, and Z. You could use A, B, and C, or you could use X1, X2, X3. The actual letters you're gonna call your inputs makes no difference to me. So here's 3 inputs coming in. And how do we figure out there's gonna be 2 outputs here? How do we figure out what the outputs are?
I forgot what the word is, but can you just add those variables to each row and then put them in the parentheses?
Yeah, we can actually do this without showing any work. We're gonna be able to directly plug it in. Yeah.
They are RM, they are just rows. And then we attribute X1.
Yeah, I mean, the way I'm gonna basically say it here, guys, is you have your matrix, right? Which was given to you. You're gonna multiply it by XYZ, which is actually written as a column. So I'm gonna put that column, right, that XYZ column right here. And I'm just gonna do the dot product. A times X, right? This is A times X. So 2X minus Y plus 5Z. I just put it right here. 2X minus Y plus 5Z. There's nothing weird or crazy that happens. And so there you go. The numbers from the first, I think this is what Amin was trying to say. The numbers in the first row just become the coefficients of the first slot. Easy, easy as that. Second row, same deal. Dot the second row with XYZ. We get 3X plus Y minus 2Z. And we're good to go. And we're good to go. Okay, that's the answer. So this is what I mean. If I give you the matrix, you can write down the transformation. And earlier before the break, we saw that if I give you the transformation, we can write down the matrix. Here's how you write down the matrix. So back and forth between the matrix point of view and the transformation point of view. They are totally in alignment with each other. Any questions on that? Seem to make sense? Feel pretty good about it? Okay. How much time do I have left? 6 minutes? You know, I actually think So I'm done with this section. I'm gonna let you guys do the rest of these problems. I just did number 20. These two remaining problems that I did not do are so easy, just like the other ones I already did. You'll get them done in 1 minute or less. It's super, super easy. So I'll let you do that. What I did find people having a lot of problems with in my morning class today was problem 2 off of group work number 9. So maybe instead of actually doing this as a group work right now, we could talk about this one, because I do think something like this could show up on Thursday, potentially. I don't even know yet. I haven't written the test yet, guys. I never write it till the last minute. I'm always just praying the printer doesn't break down. Yeah, so anyway, let me look at group work number 9. Problem number 2. Okay, so I think this is better. I think if I just go through it with you, it would be better, because a lot of people in my first class are having trouble with this. So let me write it out a little bit. You've got it in front of you there on the handout. Let's suppose that we have 3 vectors, u, v, and w. And I want to suppose, so I'm totally changing subjects now. I'm going back to chapter 5. Okay, so this was about orthogonal and orthonormal sets. So let's suppose that u, v, and w is an orthogonal set with the norm of u equal to 1, the norm of v equal to 2, and the norm of w equal to 3. So this is a problem that is kind of along the lines of that homework that I did for you in class that one time. The jury is still out on whether that was a good idea or not. Because you didn't actually have to turn it in or write it up for yourself. So I want to make sure that everybody got what they needed to get out of that. But this question is asking us to compute the inner product of 3u minus w with u plus 2v plus 2w. Okay. I would just want to first point out that what they're asking you for here is a number. When you take the inner product of 2 vectors, you always get a number. So the final answer that we're going to get out of this problem is a number. And the question is just how to come up with it. So the way you want to approach something like this is by using the inner product. Well, there's a hint. It says there's a hint. Basically, you're going to use the inner product axioms that allows you to basically FOIL this out into 6 terms. Like if you were to multiply this out, so to speak, you'd end up with 6 terms. Now this morning, I saw people doing this. They were like, so they're FOILing it out. They have 3u and u, and I saw people writing this down. Does that make sense? This is bad news, really bad news, because what's going on here is that you are squaring a vector. Has anybody ever seen me square a vector in this class? If you have, you've been hallucinating. Yes. No, there's only 2 things we can do, guys. We can add vectors together and we can scalar multiply, right? Addition and scalar multiplication. I cannot do something like squaring a vector. So that is a common misstep, I would say. What we really wanted to, what the students this morning really meant to write down was 3 times the inner product of u with u. Okay, so I can write it like that. Okay, but I cannot write it as u squared. I'm really throwing my first class under the bus right now. I probably shouldn't do that. No, it's okay. We all want to learn. We just want to learn from our little mistakes. So we take this one and we inner product with that one. Now the next one, I'm going to keep going. I have 3u inner product with 2v. And then I have 3u inner product with 2w. And as I said, there's going to be 6 terms. Let's keep going. Then I have minus the inner product of w with u. And then minus the inner product of w with 2v. And then minus the inner product of w with 2w, right? So you get all of those terms. All of those terms. Now, I guess I pulled the constant out on that first term and I didn't do that on the rest of the terms. Every single one of these 6 things in this expansion is a number. And I claim we should already know what each of those numbers is. Maybe I'll take one more step, guys, though, before I actually give you the final punchline, and then I think we'll be good to go. Can somebody? Well, let me just leave the first term the same. Sorry. So 3 times the inner product of u with itself. Do you guys remember I can pull constants out? And I can do that from both slots. So if I pull out a 3 and I pull out a 2, I'll actually get a 6. So 6 times the inner product of u and v, and then I have another 6 times the inner product of u with w, like that. And then on the bottom row, I'm gonna just write this as the inner product of w with u, and then again, I'll pull out a 2 times the inner product of w with v, and then finally minus 2 times the inner product of w with w. Okay, can anybody tell me what any of those 6 numbers are? Of course, what we've got is the question is here. Is that a hand? Yeah. The very last term, you want to give me the very last term, okay. So 1, 2, 3, 4, 5, the very last term, what are you gonna give me? So -2 times 3 squared. That is right, because this this inner product of w with itself, let me just remind everyone, that is the same as the square of the norm. Okay, so I'm totally reviewing from chapter 5 at this moment. So just to make sure, I know you guys know this, I just want to have it on the board. The norm of a vector is the square root of the inner product of that vector with itself. And so if I don't have the square root on it, like I don't have the square root on it here, then I have to like square both sides. Right? So then you just get the norm of v squared is the inner product of v with itself. So that's all I'm doing. That's all that Ian was doing. So 3 squared like that. That's the last term. Can somebody help me with any of the other terms? Yes, go ahead.
Can you just say that all like the ones that are like the inner product of u and v, the inner product of u and w, w and u, w and v are all 0 because they're orthogonal?
Okay, so not to throw my first class under the bus again, but everybody was struggling with that this morning. This word orthogonal is telling you something. It is telling you that the inner product of any 2 of them is 0. Right? So the inner product of u and v is 0. U and w is 0. And of course, w and u is the same as u and w, right? We have an axiom for that. So all of these middle terms are all 0. So I have 0 here, 0 here, 0 here, and 0 here. The only other term would be the first one. Somebody want to help me with that? I have a 3 here, right? Times, what would this be? 1 squared, right? So the norm of u is 1, and we're squaring that. So it's 1 squared. So my final answer is 3, and then a whole bunch of zeros, and then minus 18. And so that comes out to be -15. It is just a number. The final answer, when I take the inner product of 2 vectors, I always get a number. And that's how you do it. Okay? So I didn't have time to do the rest of these, but you do have the handouts. If you need something else to practice before Thursday, you could certainly look at these. I will do these in the review, I think. If you happen to come tomorrow night, I'll try to go over those as part of my review session. All right, guys. I'll let you go. Thanks for a great day. Study well. Ask me questions if you've got them. And be on time on Thursday. We'll see you for that.